Alright, so this video is going to go over the content on page 6 that we did in class that you might have missed or need a reminder of. The next page where it asks us about alloys. So this might seem like kind of a random question, but it does have to do with these mixtures we were talking about. Alloys are just a special kind of mixture, specifically a kind that has a metal in it. It could be 2 metals or 3 metals or all metals, but we can also mix in other elements with it. So as long as it's a mixture that has a metal, it's primarily metal, I believe, then that is an alloy. And some examples, brass, like we talked about before, mixture of metals, copper and zinc specifically. They melt it together to make golden-looking doorknobs and keys and instruments. If you think you got a golden key on your keychain, it's probably not gold. There is not a single atom of gold in that key. It's just brass, copper, and zinc. Same with jewelry. Most jewelry is going to be an alloy, a mixture of a valuable, pretty metal with other metals. And it's not just so that they're cheaper, although that is one of the effects that it has, but it also helps make it stronger. If you had a pure gold, 24 karat gold ring, then it would get bent all the time and chipped and nicked, and it wouldn't look as pretty long term as you want it to, especially if it's a wedding ring wanting to represent your long-lasting marriage. Well, we want the ring to last as long as the marriage does. And alloys are used all over the place in the real world to combine these properties and make our metals better, stronger, lighter in order to make them better for certain uses. So they're in rims and frames of vehicles, from cars, bikes to airplanes and space shuttles. So alloys are very, very useful. Now, most of what we're doing here on this next page is filling in some questions to this flowchart. You've got those words that we were just talking about, but we need to fill in the questions that we should be asking, help kind of organize our brain as to how to take examples of matter and end up sorting them into these 4 main types of matter. So we're always going to start by asking ourselves the first main question that's going to help us tell the difference between our mixtures and our pure substances. And if you remember when we were talking about those on the previous page, what I said the best way to tell them apart was ask yourself, is it made of more than one substance? If it is, yes, then it's a mixture. If it's only one substance though, just one thing, it's pure. You might also make a note that those things that we are looking at, if they are physically combined, those more than one thing, then it's a mixture. Sometimes we have things like sodium chloride combining chemically, and that would be a pure compound. So one or more, or made of more than one thing that is physically combined makes us a mixture. And over on that mixture side of things, the question we need to be asking ourselves to tell whether something is a homogeneous or heterogeneous mixture is if it's all looking the same. So we want to see, or if it's all looking the same, same means homo. If it does not look the same, if we can see those different substances that we know are there and mixed together, but they're visible and separate, distinct groupings, then that would be heterogeneous. So, over on the pure substances side of things, our compounds are made of more than one element, so 2 or more different elements. Of course, they're chemically combined, but that doesn't matter as much. If you just have one element, not 2 or more, then it's an element. If you have 2 or more, it's a compound. So make sure you fill in those questions into that flowchart, and it's probably going to be helpful to use this flowchart and to practice going through and asking yourselves these questions in the right order on the next couple of pages when you're working on classifying substances, because it's not just about finding those answers and memorizing them. It's about knowing the right questions to ask to figure out and classify any substance, any mixture that we give you. So these are our different types of substances. What we're going to talk about down here underneath our flowchart is how to separate mixtures. We mentioned that these have been physically mixed together and they can be physically separated, but there are some mixtures that you might not really understand. How could you possibly separate these things? You can't just pick them apart with your fingers. So it might make you think that they're chemically combined, but there are some special techniques that chemists can use to separate mixtures. As long as they haven't been chemically combined, we can separate them out using some special techniques. So the 4 different techniques are already written there on your page. So as we go through each of these slides, you really just need to write down the details, the words that I've got here. Make sure that you can tell them apart and understand the difference between them and when you might want to use one over the other. So filtration specifically uses some kind of special paper, filter paper, to separate solids from liquids. And that last part is important. We cannot separate liquids from other liquids using filter paper. It's both just going to go through the paper. And we can't separate solids from other solids using filtration, because all of those solid pieces, no matter how big or small, are going to get caught in the filter paper. So filtration specifically is made to help separate solids from liquids, and we use a special paper. This is kind of a zoomed in view because there's holes between the particles of the paper, the actual kind of filaments that are put together into that paper. There's holes. And so the big holes are going to allow the smaller particles through. The liquid generally can squeeze and move through filter paper, but then the large particles get stuck, even in big holes. If they might be able to fit through one layer, then generally we have multiple layers, multiple kind of options or opportunities to filter out those big solid particles. So solids get stuck in the paper, liquids can travel through, and that's how we separate things that we otherwise couldn't. Like, think glitter water. There technically is a possibility that you could pick out every single piece of glitter from the water, but I'm willing to bet you'd miss one, and I probably wouldn't want to drink that water if you just used your hands to try and separate the glitter from the water. But if you filter it through filter paper, then you can be 100% certain that every single piece of glitter is getting caught, and as much of that water as possible is getting through the filter. And so I would feel comfortable drinking filtered glitter water as long as it went through some good filter paper. Decantation is where we pour a liquid off of a solid. So here we're still separating solids and liquids, but we're not using special paper. So usually this just kind of relies on the fact that our solids tend to be more dense and like to stay at the bottom of our cup or our beaker that we're pouring them out of, and our liquids are fluids, so they can move and flow, and so we can pour the liquid off the top of the solid without it rolling out. I always think of this as if you cook at all, you often have to open up some cans, and you probably have to decant some of the liquid off of the top of like black beans or something, so that you don't have all that liquidy stuff poured into your casserole or whatever you're making. So you can just kind of gently pour it, and the liquid will slowly pour off the top, and the beans will stay in decan as you decant the liquid. Now, distillation is a pretty fancy process, but it's a pretty simple idea that it's based off of. And we use distillation to separate 2 or more liquids based on their different boiling points. And they have to have even a slightly different boiling point for this to work. Because what happens, if we start with a mixture in this container of more than one liquid, then we heat up that container with both of the liquids in them so that it's between their boiling point, meaning above one of their boiling points and below the other's boiling point. And what that does is that the liquid that boils at that lower temperature is going to start boiling, but the one that boils at the higher temperature that we haven't reached yet will not boil. And so the boiling liquid will turn into a gas, and those vapors will go through a system of tubes where they're going to be allowed to cool back down, and then we can have our liquid again at the end, but it's now been separated because we force it to turn into a gas, so that as a gas we can separate it from the liquid, just because they like to flow and move and rise compared to our liquids. And so that's really all that distilling is using the fact that most liquids will have different boiling points. We heat them to right in between those boiling points, and we can boil one off while leaving the other one. The higher boiling one will still be left behind in that original flask. So we'll be able to get our two different liquids in two different flasks. And finally, chromatography. And chromatography is, like the prefix chroma implies, separating molecules based on the difference of attraction of these colored particles. Chromatography does generally need to be some kind of color-based separation, but the colors aren't why the separation is happening. It's more of the fact that because they're different colors, the molecules are different shapes and sizes. So really, the shapes and size difference is causing the different colors that we're seeing. And because these particles are different shapes and sizes, when we put a dot of this substance, this mixture, on a piece of paper and dip it into some kind of solvent, something that will dissolve the substances in that pigment, as the water level rises up, or as the solvent level rises, it's going to dissolve the pigment. But if this is a mixture of pigments, of different molecules, then some of those molecules are going to be better dissolved, better carried by our solvent liquid than others. So here you can see the lighter colored ones seem to be going farther. So the lighter colored ones are almost lighter, easier for the liquid to carry, so they're getting carried farther. The darker ones are heavier, so they seem to be getting dropped a little bit sooner. And the longer we leave that in our liquid, then the more of that separation that we're going to see. We definitely have more of the lighter stuff going farther and the darker stuff staying behind. So this is a color-based separation, but it's really a little more complicated chemistry kind of going on behind the scenes. But it is a way that we can separate mixtures, kind of by differences in which ones will dissolve or not, and the differences in their solubility there. So these are our methods of separating mixtures, which is where our notes are done. But if you haven't already taken the time to get started on worksheet 1A, which is the next 2 pages, then that is what we did next in class. And it goes all the way from physical, chemical stuff that was in that podcast 1.3 I talked about earlier, all the way through to this element compound mixture, classifying things with that flow chart, finding element names on the periodic table or from our element list, and, just listing the indicators of chemical changes. So all good stuff, all stuff you're going to need to be able to do by the time we get to our test. So if you haven't already tried these out, go ahead and give them a start. Let me know if you need help checking your answers. I have given you a few hints on Canvas, but if you need any help or if you can't find those hints, get in touch with me.